All right. Hi, everybody. Welcome back to office hours. So today we are going to do this quick warm-up, and this entire warm-up is going to encompass all of Chapter 8. So that's great. So essentially, if you know how to do every single one of these warm-up questions, you guys are golden up into the new material that we'll talk about today. Okay. So I hope you guys took a few minutes to look at these, try these on your own, and let's check your answers and see if you're right. And just to give you some incentive to try these problems on your own. These were all from various old exams that I just pulled from. So every single one of these questions that you see were all asked on an old test. So these are probably important questions to be able to do. So the first question is A. So it looks like we're doing hydrohalogenation, but remember under free radical conditions. And remember, we have the peroxide present, okay? That's the difference. So before, we've had, just an alkene starting material with HBr, and now we have an alkene starting material with HBr, as well as the peroxide and heat present. So that's what forces this to go into the radical mechanism, not the just regular alkene addition reaction, okay? So basically what we need to know is that we're doing anti-Markovnikov addition. So the bromine is going to add to the less substituted side. So our choices here clearly are a tertiary side, okay, tertiary. And then here we have a secondary. So it's kind of obvious that you're going to get bromine addition at the secondary position, and it's chiral at that position. So we could draw both mean enantiomers. So, and I think Dr. Peterson, if I remember correctly, I'll tell you 1 second. Technically become chiral here as well. Actually, no, you don't. Never mind. Don't listen to me. Okay. So we're here. Those are my two main products. Okay. So B. So B is just free radical bromination conditions. We know that bromination is, regioselective for the more stable position for reasons we've talked about. So out of all of the positions around this cyclohexane, I see that I have this quaternary position over here, so quaternary. And then over here, I see I have tertiary. So my next issue now is, can I abstract a proton? That's what happens in these propagation steps. So can I abstract a proton from the quaternary position? No, there isn't any. So the only possible thing is to abstract the proton from the tertiary position like we see there, and we get the bromine adding at that position. No, we go through this main intermediate. And I think somebody asked this last class, where we go through the radical intermediate. So we went from sp3 to sp2. So now we don't know what the chirality used to be, okay? So the chirality, meaning that methyl substituent, is no longer, let's just say that would be 1, 2, so no longer S, okay? So now we can get a racemization is what we call it at this radical position where the bromine could be either a wedge or a dash. So we get the two main diastereomers. So essentially we get the bromine adding in here, or we could have the bromine adding on a dash. Okay, but you keep the configuration of this center the same. Okay, so those two diastereomers are formed. Okay, I missed my dinner. Do you think you'll post this weekend over Thanksgiving break? Yeah, I guess that's fair. Probably the first, so you guys can all do it over Thanksgiving break. I'll probably do it this weekend. Okay, next one, NBS and H-nu. So that is a Lilac bromination. So we know that, we don't know the mechanism, but we know that, I think some key things to just go over real quick is that N-bromosuccinimide has this Lewis structure, probably should know it. It comes from succinic acid, okay? So that would be a 4-carbon carboxylic acid. And it's succinimide because it's an amide, and bromo because the bromine is attached to the end. Okay, so that's where that name comes from. And this bond is the really weak bond that gets homolytically cleaved. Remember, 1 electron on each. So we generate the bromine radical from that source. Okay, just something to keep in mind. That's kind of the main step you need to know. Okay, so what happens is you're going through an allylic radical. So there's 2 allylic positions. We have allylic position, let's just call this A, and allylic position B. That just means 1 carbon removed from the alkene. Okay, so essentially, again, the radicals, in order to get a radical somewhere, you have to get a proton removed. It's proton abstraction, right? And I don't see any protons on position A. It looks like we already exceed our octet. So there's no way that we could form a radical at allylic position A. But on position B, there's 3 protons. So yeah, we can form that allylic radical there. So let me just draw our main intermediate. Our main intermediate is actually this allylic radical. So whenever you go through this reaction, and it's only reaction C, allylic bromination, you have to consider a possible resonance structure with respect to the alkene. And the reason that is alkene substitution is really important in terms of intermediate stability. Okay, so if our alkene is more substituted, then our intermediate would be more stable. So let's consider an alternate resonance structure. Let's say I put one of those electrons in there, one of the pi electrons, forms that double bond there, and then the alternating structure would be, something that looks like this. Okay, so let's classify the substitution pattern of our alkene, right? So this alkene would be a disubstituted, okay, disubstituted geminal, okay, and then this one is also disubstituted geminal, but my problem is there was no difference in substitution. So why would I rearrange? There's no reason to rearrange. And also you wouldn't get a different product in this situation, but there would be no reason to rearrange because there's no increased difference in stability from that rearrangement. So essentially you can just go ahead and use that intermediate that you originally drew, and then you can imagine that this bromine radical is going to hit that, alkyl radical and then form a bond there. So your end product should be that. Okay, so these are our answers. Okay, that's a pretty good summary of how to do these reactions. Okay, let's do step 2 or question 2. So given the free radical chlorination reaction below, what is the statistical yields of the 2 possible product forms? So that's butane. We're subjecting it under free chlorination conditions. And let's think about that. So there's clearly 2 different products arising from 2 different substitution points. And I think that's the key. We have a secondary position and we have primary position. So of the 2 secondary positions, so these are the 2 secondary positions, how many protons are there? Okay, so let's just draw those in. Okay, so of those 2 secondary positions, how many protons do we all see? In the chat box, anyone? 2 each, right? So we see a total of 4, right? Yeah, great. So we see 4 secondary protons, okay? So then out of the primaries, so I'll draw that in red, so the primaries are over here. Okay, I see that I have exactly 3 on each of those, 3 on each of these. I just want to draw these in so you all see what I'm talking about. So that would be 6 tertiary protons, okay? So we see that we have 6 tertiary, I keep saying that wrong. So many numbers. 6 primary protons and 4 tertiary. I do it again. 4 secondary protons. Wow, my brain is scattered. Okay, so how many total protons are in this structure? Well, there's 10. Okay, so this is the secondary product. Okay, so how many possible protons do we have to work with? Well, there were 4 of them. Okay, and then for this primary product, we had 10 total, but we could only use 6 of them. So the ratio would be 4 to 6, or if you guys like math, 2 to 3. And yes, this was asked before. Okay, so make sure you know how to do that. Now, if you had a circle, let's say, between product A and product B, which one would contribute to a higher percentage of the product solution? What would it be? A or B? Okay, so everyone's kind of wrong. It's A, actually. It should be A. Remember that the more stable radical, okay, so the secondary radical would be the intermediate for that product. And then for this one, the intermediate would be the primary radical. So remember, radical stability parallels carbocation stability. And here, the secondary radical is more stable because of extra hyperconjugation from those alkyl groups. Okay? Do you guys all feel better with that? Everyone knows why it's A now, or people are still confused? Okay, I'll say it one more time, Caroline. Okay. So essentially, statistical is just based on like theoretical practice. Like there are 6 of these primary protons available. There are 4 of these secondary protons available based on pure statistical ratios, like not based on like any other like actual chemical laws. Like you should get like for every 2 products of this, 3 products of that. Like that is basically what that is said, okay? However, if I were to ask you the next question of like which one in practicality actually forms, well, we know that the radical intermediate that comes from both of these products are the secondary and primary radicals respectively. And we know that our radical trend follows into the stability, that follows carbocation stability. So because we're secondary here, we have 2 adjacent alkyl groups that can hyperconjugate and stabilize that 7, valence electron center. Whereas here, we only have, 1 alkyl group that can stabilize the center, okay? So that's why this one would be slightly more abundant in our reaction mixture, okay? Okay, so it seems, I think we're good. I think that was good. Okay, so that's pretty much it for radical chemistry. That's all you need to know for chapter 8. Does anybody have any questions on that so far? Okay, so essentially, we're going to go to the critical thinking real quick and just talk about the few critical thinking questions we have, and then we'll move on, okay? So I'm going to share my screen. If you guys don't have it, these are the critical thinking problems. Okay, so I would be definitely aware of how to do this. Okay, so just give me 1 sec. Get this. Okay. All right, so we have this reaction coordinate diagram. I think, okay, so you guys got it on what page? 97, I think. Okay, so I hope you guys can also still see my paper in case it's not clear. So just make sure you can pin this video from this other screen. Okay, so we have the reaction coordinate diagram below with toluene under free bromination conditions. Okay, so toluene is actually a solvent that you will come into contact in the Orgo lab. It smells pretty crazy, pretty actually nasty, honestly, but it's a liquid. Okay, so essentially we want to draw the structures / molecules that are rising at position A, okay, on the reaction coordinate diagram. So whenever we do these problems, I always think it's a good idea for you guys to just draw out the full mechanism because it's kind of unclear just to jump into the reaction coordinate diagram where we are. So essentially, I'm going to draw one of the protons in at the benzylic position. And, we have Br2 and it looks like heat. So we know for initiation, okay, we have this. 2 molar equivalents of bromine radicals forming. But notice that this question says this is showing the propagation steps only, okay? Notice that it says, oh, where are you? Where's the marker? Here we go. Oh, okay, cool. Propagation steps, okay? So this does not count on the reaction coordinate diagram. But next, remember the first step would be proton abstraction. Okay, so we took one of those radicals and it abstracts a proton, okay? So we generate the benzylic radical, okay? So this is benzylic radical, that's one. We also generate HBr, okay? And then that was just, remember, the first step of propagation, but we always talked about there being a second one. And so we'll take the product, that intermediate generated, the benzylic radical. And remember, I said you always have to show it's Br2 coming, not another bromine radical, because the whole point of this step is showing that you're forming more bromine radical, okay? So essentially, oops, why is this? Where's my mouse? Okay, so essentially the products of the first step are kind of obvious at this point. So for A, you have this benzylic radical, okay? You have this waste product, HBr, and then you also have Br2, okay? Do we all see that? And then what was the result of this step? Well, remember, it was the actual product that was formed and more bromine radical, okay? So you can see that after step 1, these are the 3 products that I circled. You have the radical, you have HBr, and you have Br2, okay? So then for B, it says, draw the structure of molecules that corresponds to point B. Well, this end product of propagation, remember, we're only looking at propagation here. Well, the end product of propagation would be these two, right? So those two structures, all right? So that's it for A and B. So then for C, it says, which transition state, 1 or 2, is encountered during the rate determining step? What do you guys think in the chat box? For some reason, I can't. Where's the chat box? Okay, there we go. Yep, I see a whole bunch of people saying, what is it? 1, 1, 1. Yeah, good. So yeah, it's transition state 1. So remember, the rate determining step corresponds to the highest energy barrier, and that would be clearly transition state 1. Okay, so D, if chlorine were used as a reagent, how many unique products would be formed? Okay, well, think about how many possible protons are there, okay? So for D, let's just draw that out. Okay, so this is what toluene looks like. Okay, which protons are capable of being abstracted? Okay, which ones? 1, right? Any of these are equivalent. So remember, we don't touch benzene until orgo 2. Never ever touch benzene. So none of those protons are going to react. Only these protons are going to react at the methyl position or the benzylic position. So you get one exclusive product, which is the one we see. Okay, so again, for this question, it wasn't too difficult. You just have to basically slow down, realize where you are, and take a step back. Okay. That's that one. Let's move on to the next critical thinking question. Okay, so for this one, we're on this next reaction. You can tell, I think Dr. Peterson really likes these reaction coordinate diagrams for radicals, so just make sure we're all good here. So provided below is this reaction. It's an allylic bromination reaction with 3-methyl-cyclohexaenone and N-bromosuccinimide with light present as the initiating source. So again, same exact thing. So let's just draw, you know, our main starting material. Again, initiation isn't present, so I'm just going to write, just for all intents and purposes here, NBS, light, and for the initiation, it was NBS. We'll do that, and we'll show that we have the bromine radical and then an N radical, and we'll say R, okay? So this is initiation, and this is not shown in this plot, okay? So next is going to be the propagation steps, okay? So for A, draw the intermediates at position A. Okay, well, we know that we're going to go through this allylic radical, okay? So where are the allylic positions? And remember, there are 2, but only 1 makes sense, okay? So I will basically give you guys options. Here's A, and here's B. In the chat box, out of A or B, which position is the better one to obviously pick? Okay, so no, guys, the answer is actually A, okay? So let's talk about this again. Okay, so essentially, it's A because what you're trying to do, the whole reason we're doing this resonance shift is because, let's say when I go to this B, let's just pick B, for example. This is the wrong answer, okay? So let's say I picked this radical, okay? So that's essentially what you guys chose. And I showed the resonance structures that, you know, result from doing this move, okay? And your resulting structure basically goes from di substituted for the alkene to di substituted again for the alkene. Okay, so there was no difference in substitution with respect to the alkene. So there was no increase in stability here. But let's pick the A position radical. Okay, so let's pick A. Okay, so if I pick A, and I showed the resonance move, so here, oh, did I pick that too far away? I'm sorry, this is too far away. This is my bad. Oops. I should have picked, that is A. But still, same thing applies, okay? So might be, maybe that's why you guys were getting confused. Sorry, this one, but still, same thing applies. So essentially, this radical goes in, this radical goes in, this radical comes out. So essentially, you get 2, 2, 2. Okay, so you get that. Okay, so what happened was you went from the di-substituted alkene to the tri-substituted alkene. So it's better in terms of alkene stability, and that's why we're going to pick allylic position A. Okay, so essentially draw the intermediates at position A. Well, the intermediates would be the original allylic radical I picked, so it would be that, okay? And then also the resonance version, because the resonance is not an actual chemical step, that's an internal rearrangement. So this one, okay, and you could also say the resonance version of that. So, okay, so this is the answer to part A, and it corresponds to the intermediates that are present at part A. Okay, position A. B, draw the major stereoisomers that result from the next chemical step. Well, that's easy. That would just be bromine coming in where the radical was. So if this is my better structure, then you can tell that bromine there plus bromine. Remember, it's sp2, so you can have a tag at the front or the back base. So those are the two main stereoisomers for part B. Okay, and then C asks, what does the energy barrier C refer to? Okay, so what does it mean when you are basically trying to form a radical, okay, from an already existent bond, okay? Remember, we are cleaving this homolytically. So when you homolytically cleave a bond, that energy that is released, or the energy barrier associated, if you need one, it's bond dissociation enthalpy. Great, okay? So does everybody have that kind of connection now? Bond dissociation enthalpy is the energy it takes to endothermically, essentially, it requires energy to homolytically cleave a bond or form radicals, okay? So clearly in part A, after the initiation step, you're trying to form a radical on the main alkyl, group that you have, the main carbon group that you have. So that is the bond dissociation fee. It's the amount of energy that it takes to form these radicals. So C would just be BD. All right. I hope this is making some sense to you guys. We're gonna just do, I think, is there one more? Okay, yeah, so let's do this one. And I think we've already kind of talked about it, but a nice summary of the whole kind of chapter. Okay, provided below is an energy plot of the bond dissociation enthalpies with 4 distinct energy levels, obviously not drawn to scale, but just qualitatively, based on the BDEs of the protons indicated right in the level that corresponds, right in the letter, that corresponds to the relative energy level. Okay, so we've already done a problem that's similar to this, so you can imagine looking at all the structures to the right and basically scribbling out where it says HA, HB, HC, HD, and just drawing a radical at that position. So I'm going to do that over here. So that's HA. That's HB. That's HC. Oh, also, I have a quick question for you all. I mean, I know that not a lot of people are in here. I don't necessarily, obviously Dr. Peterson isn't doing Orgo 2, but I do have, like, in the orange workbooks that you guys have right now, I wrote an Orgo 2 version for when we teach Orgo 2. And although you may not have the same professors, and although you may not have, like, your professor use it, would it be possible if you guys want it through Target Copy and I can just, like, maybe, like, make it available? And then, like, it could just be practice, I think. Okay, there you go. I just looked at the chat box. Okay. I'll talk with Dr. Peterson because I just thought about that. I mean, at least that could be like me coming with you, even if I'm not. We do have a key already written from like previous semesters, kind of just exactly the way that you see it. So I know I can't move on, but essentially I do have my YouTube channel. So with all the Orgo 2 videos already on there. So like I still am with you. And if you get this workbook, it will be good. So I don't know. We'll see. Let me talk to Dr. Peterson and I will see what she says. Okay. I just thought about that tonight. So essentially HD, let's go here. So we're there. Okay, here. So now we just have to think about all the trends that could potentially stabilize these radicals. Okay, so here we have a plain secondary, no stabilizing features. Here we have secondary, but we also have induction. Okay, so that's like not so great. That's destabilizing. Here we have secondary, but secondary with resonance, so that's pretty good, secondary allylic. And then here it looks like, oh, we have tertiary, and not only tertiary, but we have tertiary allylic. So I think it's pretty obvious in terms of the relative stability patterns of all of this. Okay, so in terms of E1, okay, so E1 would be the smallest bond dissociation enthalpy. And remember, the smallest bond dissociation enthalpy refers to the radical that is relatively stable. And that should make sense. Think about it. The amount of energy it takes to homolytically cleave that bond is relatively low because the products that form are really happy and stable by themselves. Whereas whatever corresponds to E4, that's basically saying so much energy has to be thrown in to make that radical because that radical that forms is so unstable on its own, okay? Because it's unfavorable, exactly. So essentially, let's just kind of draw a mini plot, okay? We'll just do like A, B, C, D, or something like that, 1, 2, 3, 4, okay? And I guess the lowest energy would be the most stable, so that's probably HD. I would think HD is right there. And then on energy plot 2, level 2, it would probably be secondary Lilac, so HC. And then above that would probably just be HA, the plain secondary. And then above that would be the worst one, so secondary and with induction, HB, E4. Okay, so I think that's kind of important to note. Okay, so let's answer these quick questions. So these quick questions are gonna basically reflect the energy plot that we just made. So A says the proton with the greatest bond strength. Okay, so greatest bond strength means that has the highest bond dissociation enthalpy. Okay, so that would be HB, right? Corresponds to E4. All right, so B says the proton with the weakest bond strength. Okay, so the weakest bond strength is the one that had the smallest bond dissociation enthalpy. So that would be HD. Okay. C, the strongest carbon-hydrogen bond. Okay, well, the strongest CH bond is going to be the bond with the highest bond dissociation enthalpy. So that would be HB again. And then the longest carbon-hydrogen bond would be the weakest bond. So that would be E1, okay, or HD. Okay, so you can see we can ask a whole bunch of different questions for these. Make sure you guys understand all that. What is that popping up? Do you see that? Whoa, it's so weird. Anyway, so that's pretty much it. And I think that wraps up this chapter. Okay, so let's take a couple of seconds. Everyone take a break, get a glass of water, and yeah. Okay. Let's see. And we're gonna jump into chapter 9 in a second. Let's see, I have some questions on 10 and 11. Should I wait to the end to ask? Yeah, Caroline waits to the end. Abby, longest bond equals weakest bond equals lowest BDE. Correct. As we forward, can you please go over a part of this? Oh, of course, yeah, Keisha, we're definitely gonna go over that. Okay. All right, so hope everybody is back. We're gonna just jump into this new stuff, okay? So I hope you guys are pretty okay with the radical stuff. I think it's relatively easy compared to what we're about to do. Okay, so first we're gonna just go into a little bit of theory, okay? So let me get some paper. and we'll do some review. Okay. So essentially what chapter 9 is, okay, it's called Nucleophilic Substitution and Beta Elimination. Okay, and essentially there are two different competing reactions, what we call pathways, that could happen, and we can induce one pathway over the other basically by manipulating the reagents and the conditions that we're in. So for example, let me think about this example. Okay, so let me just, draw this. I'm going to draw this, and let me draw two different things. So we have, this haloalkane, okay? And let me just show, okay, let's just try this. And this is just me making stuff up for you guys, okay? Okay, and I know you guys don't know all the details yet. But essentially, notice, I have the same reagent, sodium hydroxide, right? I have the same starting material for both. However, I have two different, other reagents, or basically these are solvents, water or DMSO, and we'll talk more about that. And essentially what happens is under one pathway, I get one product, and under the other pathway, I get another product. And that's weird considering that I have the same main reagent and same starting material. So essentially, with this example, you get this product, okay? And with this example, you get that product, okay? So how come we get these two different products? One's an alkene and one is an alcohol, okay? So what happened here, this was the nucleophilic substitution product, okay? And this is what we call the beta elimination product. And the whole goal here, okay, at least up in for now, is to basically, when you're given, the starting material and you're given different reaction conditions, can you predict, am I getting beta elimination? Am I getting nucleophilic substitution? Am I getting a little bit of both? And that's basically this entire chapter, okay? So do you guys kind of get the logic so far? It's similar reactions, similar reagents. However, there are going to be subtle things that we're going to teach you that are going to help you distinguish between this one and that one, okay? Or sometimes when you have both of them. All right, so let's basically just talk about the first branch. So we're just going to stick with today. We are just focusing on nucleophilic substitution. So this is today. And then next Monday, we're going to finish this whole chapter with the beta elimination side. So today we're going to focus on the nucleophilic side, and then we'll do beta elimination in the future, okay? So essentially, the first things I want to talk about are the two types of main reactions, Sn1 and Sn2. So I guess I'll just do it like this. So let me move this. Can we add more people into the Zoom? Okay. So here. So essentially we have two main reactions. So we have Sn1 and Sn2. And we're just going to talk about a couple of different things with these. So for Sn1, what does that name reflect? Well, it stands for, you have to read that, I read these backwards. So it's unimolecular from the one, nucleophilic substitution, okay? Bimolecular, nucleophilic substitution, okay? So I'm just gonna write that down. Unimolecular, nucleophilic substitution. And for this one, it's bimolecular, nucleophilic substitution, okay? So we kind of follow that so far. Unimolecular, so clearly one molecule is involved, and this one would be bimolecular, okay? So essentially, how do we know what happens in which pathway? So for Sn1 pathways, some things we just need to consider. What's going to happen is something called the leaving group, which I'll abbreviate as LG. Okay, the leaving group leaves on its own without any reagents. Okay, and that's the key. So maybe that answers a little bit of your concerns regarding why is it unimolecular? Well, this fact right here, the leaving group, which we don't know yet, is going to leave on its own without any reagent necessary. So that's why it's only dependent, this reaction is only dependent on one thing, or one molecule, the main molecule with the leaving group, okay? Then what happens when that leaving group leaves? Well, when that leaving group leaves, we're gonna form a carbocation intermediate. And trust me, I know this may not make sense now, but it will once we start doing practice. forms a carbocation intermediate, okay? And what's the consequence of forming a carbocation intermediate? Well, you're going to have racemization, okay? So we'll call it racemization of your product, okay? Of your products, okay? So basically means you're gonna get both enantiomers, okay? So if I'm going through a carbocation intermediate, let's think, okay, let's see who's like really like intellectual here in the chat box. If I'm going with carbocation intermediates, like, doesn't that give you a little bit of a clue as to what types of carbon starting materials I have to deal with in terms of substitution? If I have carbocation intermediates, I'm probably dealing with, do you think more substituted or less substituted alkanes? What do you think? More or less? Okay, we're kind of split. What do you think? I'm talking about, let's say I have a haloalkane. Let's say I have what we had above, this bromine guy. Do you think I'm dealing more with more substituted haloalkanes or less substituted haloalkanes based on the things I talked about here? And you guys know it. You guys definitely know it. More. Yeah, you guys got it. More. So if I'm talking about carbocation stability, right? And then I always get FaceTime calls. Sorry. Okay, smart. Sorry about that. So essentially, if we're thinking that we're going through a carbocation intermediate, those things that form that, meaning a tertiary or secondary leaving group, would probably be best because, you know, the hyperconjugation effects that exist. So basically, we can just say that we're limited to substituted starting materials. So again, this whole section is a lot more conceptual than any other section, and even in Orgo 2, in my opinion. I think this is probably one of the hardest chapters. I say this and people don't, some people agree, some people don't, but I think this is the hardest chapter in all of Orgo 1 and 2, personally. So if you get through it, you'll be good. So that's basically all the considerations I want to consider for Sn1, okay? So for Sn2, we're at bimolecular nucleophilic substitution, okay? So now you could basically think it's the contra or the opposite of everything you saw with Sn1. So here, the leaving group, that's it, sorry, limited to, yeah, I kind of got, limited to substituted starting material. Substituted starting materials, okay? So bimolecular nucleophilic substitution. So essentially, the leaving group does not leave on its own. So it's the same thing, but does not. So that double tick means the same thing, but does not leave on its own. Okay, that's why it's bimolecular. You need something else to do that, and that's the main reagent. Okay, we don't form carbocation intermediates. Actually, we don't form any intermediates here. We actually form a transition state. So we're going to say forms a trigonal bipyramidal, and I'm going to make this make so much sense. Forms a trigonal bipyramidal transition state. Okay. And what's our stereochemistry that we're dealing with? Racemization. No, we're not getting racemization. Instead, we're going to get inversion of configuration. Okay. Okay, inversion of configuration. So R to S or S to R, essentially. Okay, so then now if we're thinking, well, we're not going to go through a carbocation intermediate, and those reaction pathways are limited to pretty substituted starting materials. What do we think Sn2 is going to do? What are we limited to? Probably less substituted, right? Yeah, so we're limited in this pathway to less substituted starting material. Okay, so now some other things to just maybe add. Like, again, this is me summarizing the whole chapter. Okay, so this is a good thing. So summarize some things. For Sn1 conditions, you need a relatively weak nucleophile. Okay, and you also need protic conditions. Okay, here you need relatively strong nucleophile and aprotic conditions. and that's chapter 9, part 1, okay? So let's kind of just review all the things that we talked about. So there are 2 competing pathways that we're going to be talking about today, okay? In terms of, so let me just also break this down. So there are 2 main branches. There are nucleophilic substitution and beta elimination. Where do those come from? Well, the nucleophile here was the hydroxide, right? And it substituted something else. So it's substituted in the place of the bromine. That's called a nucleophilic substitution, okay? So today we're going to talk about the 2 types, okay? So that's Sn1 and Sn2, okay? This is called beta elimination. So whatever, this bromine is my leaving group, which we'll talk about in a second. Bromine is my leaving group, so it's going to leave the molecule. And that's called, and whatever carbon that's attached to is called the alpha carbon, okay? So 1 carbon removed is the beta position, okay? So you can tell that this is a beta, probably dealing with some beta chemistry there, beta elimination product, okay? So essentially what's going to happen is that this hydroxide is going to act as a base, okay, not a nucleophile, we'll talk about it, okay? Removes the proton from here, pushes the electrons there and facilitates that out. So essentially you can see that we're going to talk about the 2 types of beta elimination, E1 and E2, on Monday, okay? So today we're just going to be here, Friday or Monday, whatever's next is there, okay? Let's kind of just, everyone take a screenshot and let's just do some problems, and that's the other way we get good with these, okay? Cool. So everybody take out your phones or open up another tab if you can. And I'm gonna do a fun activity with you guys. Everyone loves this. So I have to figure out how to play like intuitive learners of a video in your class, assign a challenge. I don't know. Teach? Classic? Okay. Do you guys see this? You guys know how to do this stuff? All right, so cool, people are joining. All right, so I do this every semester. I think this is like the easiest way to just talk about, oh, you guys need the, some people missed this here. I don't know if you guys can all see this. So I do this every semester. Everyone loves it. We basically just talk about, like, as we go along, how to distinguish between Sn1 and Sn2. So we're not even going to draw any products right now. So right now, everyone just take a step back, and we're just going to, I'll leave this chart up. I think you can still see my notes, right? Hopefully. Yeah. Okay. So I'll leave this up. And once everybody joins, we can just go through these, okay? Again, optional, you don't have to, but it's fun. Something different. Caroline, would you say, should we write this down? No, because I think I repeat a lot of these questions in your student workbook, so yeah. Okay, we're gonna start. So essentially, let's click go. Where's the start button? Oh, there it is. Okay. Again, there's a speed factor in there, so the faster you are to answer, the more points you get. Okay, Sn1 or Sn2, we're ignoring elimination for now. Okay, so the first thing you want to do is consider the substitution of your haloalkane or whatever your leaving group is. So here I would say it's primary, okay? And then after that, you have to ask yourself, do I have a strong or a weak nucleophile? And then you ask yourself, what is my conditions? Am I protic or aprotic? And I'll go over that once we have it. Okay, great. Okay, let me just talk about this. So the first thing you have to ask yourself is, what is the substitution, okay? So clearly this is a primary. Primary falls under the Sn2 category, okay? It's less sterically hindered, so we were already liking Sn2. The next question you ask yourself, am I strong or am I weak? Okay, so once you dissociate the sodium from the thiol, okay, so you NaSH, you get a full negative charge on the sulfur, right? Does everybody see that? Anytime you're fully negatively charged, you're strong, okay? When you're not charged, you're weak. So for instance, water versus hydroxide. Water, you're weak. Hydroxide, you're strong. Anytime you're charged, you're strong, okay? So this is a strong nucleophile, and DMSO is polar aprotic conditions, okay? So all of that tells me Sn2, right? Aprotic, relatively strong nucleophile, and sterically unhindered, so Sn2, right? What's my substitution? And then you have to ask yourself, is it strong or is it weak? And what are my conditions for my solvent, protic or aprotic? Okay, so good job. So you guys see that this is a tertiary starting material. Then basically you can imagine that this leaving group could leave on its own. You get some sort of carbocation intermediate. It's pretty stable at the tertiary position. And then now we have water. Water is our main reagent, okay? So that is a weak nucleophile. I don't see any charges. And it also serves as the solvent. So it's a polar protic solvent. So yes, Sn1. Okay, so. Okay, so yeah, this one's a little bit more tricky. So the secondary is what we call the gray area region. So I'm gonna go over, actually I can do that real quick. So if you can look at my like pinned paper or pin screen, whatever, and you can see this. Basically what I wanna draw is this graphic. So H3C, X, let's just call this C, X, R, let me just call it. Okay. So essentially you can see that this is a basically primary. Okay, so X stands for leaving group, R stands for just carbon groups. This is primary, this is a secondary, and this is a tertiary. Okay, so essentially you can imagine that from, let's just draw here to here. Okay, these are technically considered more substituted. So this is my Sn1 pathway, okay, from here forward. From here backwards, that would be the Sn2 pathway, okay? So what happens is you can see there's this great degree of overlap with the secondary, okay? So essentially a good trick for you guys on your test when you guys are starting to do these reactions is anytime that you have a tertiary, it's always Sn1. Anytime you have a primary, it's always Sn2, okay? Secondary, you have to slow down a little bit and you have to look into the type of nucleophile you have as well as the type of solvent you have, okay? So when we look at when we look at this like ester, if we take away the sodium, we get a full negative charge on that oxygen. That makes that a strong nucleophile. Acetonitrile is a polar aprotic solvent. So basically it shifts this to the Sn2 pathway. So it should be Sn2, okay? We'll keep talking about these. Okay. So tertiary, no thinking, okay, based on what we just drew. Tertiary, no thinking, always, 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 always based on the graphic you see. Okay, good, better. So Sn1, right, so we are tertiary, which means we're kind of on this realm, okay? The nucleophile is weak, and it also serves as my solvent. It's a protic solvent, it has protons in it, so yes, Sn1. Good job, Brian. Okay, so this ester is my leaving group. This carboxylate anion is the leaving group. And classify that substitution. This is another easy one, okay? So again, We know the substitution of the leaving group. We know this is either a strong or a weak nucleophile. It also serves as the solvent here, okay? All right, we're a little bit more tricky. Okay, so look, this is tertiary, right? This is the tertiary position, okay? This carboxylate anion is on a carbon with 3 other carbon substituents. So we're already thinking here, Sn1, okay? That's a weak nucleophile. There's no charges on it, okay, weak. And also, there's protons on that. So that means it's a polar protic solvent. All of those things fall under the Sn1 category. Polar protic, weak nucleophile, substituted starting material, okay, Sn1. We'll do one more, and I think we need to just look at some more theory because, you know. Okay, so this is a secondary, okay, so we're thinking we're in my gray area, right? So, or my red area, I should say. I don't necessarily know. Now I have to look at my reagent. Is it strong or is it weak? Okay, it's definitely a better, okay, this is better. It's definitely a strong nucleophile because once the sodium goes away, you get a negative charge on the azide, N3 is azide, so you get a full negative charge there. And then DMF is just a polar aprotic solvent. So aprotic, strong nucleophile, secondary tells me Sn2, okay? Let's stop here. We can continue Kahoot maybe like tomorrow or something, because I think we need to just do some examples of this, okay? So essentially, yeah, let me go over those things. So let's just consider an example of Sn1 and Sn2, and then we'll do some more quick problems later. So the first one I want to consider, let's just say, is this. So I'm just going to do a generic example. So we have this, and I'm going to subject it to methanol. And basically, we need to know what pathway we're doing, okay? So essentially, what we see is we have a tertiary haloalkane, okay? So it's tertiary. So tertiary, in my mind, is already making me think Sn1, okay? And what we talked about with Sn1 is it's nucleophilic substitution and it's unimolecular, okay? So everybody listen to the words. It's unimolecular, which means that it's only dependent, the whole reaction is dependent on this leaving group leaving on its own, okay? So it makes sense for that to be the first mechanistic error. This step is independent of this reagent, okay? That's why it's a unimolecular reaction. So the first step is just this leaving group leaving on its own spontaneously, and you get where that bromine was, a carbocation intermediate. We've talked about this already. Now your main reagent, your methanol, can come in and attack that deficiency. This is just like a normal, you know, like an acid catalyzed ether synthesis, you know, reaction. And you're basically going to get addition, nucleophilic addition, okay? And the exact same series of steps, you know, we've seen before with the ether synthesis. Okay, so you get this ether formed. Okay, so essentially that's the product. So this is Sn1, okay, Sn1. So it was nucleophilic substitution, unimolecular. What happened was, let's say this was a wedge methyl group here. Let's say there was a wedge methyl group here. We would get 2 major diastereomers, okay? So because we would be chiral at that position, so we would have to consider, you know, that's the consequence of going through a carbocation intermediate. The fact that we could get 2 major diastereomers. Okay, Sn1 products, okay? That would be an Sn1 example, okay? And why is this? Well, this is a weak nucleophile, okay? And why do we want weak? Well, we want weak because if it were strong, we would be so eager to replace this bromine that it wouldn't be unimolecular. You wouldn't go through this carbocation intermediate. So essentially what that means is, like, if I had a strong negative charge, like hydroxide, whatever, it's just going to come in and immediately attack with the bromine still present and then try and remove the bromine. And that's not what we want here. We want it to form maybe exclusively these 2 diastereomers. So in order to promote it through this pathway, we're like, okay, let's use a weak nucleophile so that it gives this bromine its time to remove itself. The bromine will remove itself in time because it's weak. Then this nucleophile will add, okay? And then you get the racemic mixture going on. Okay, so that's that. Next, let's try an Sn2 example. So let's just take let's just take let's just do that, and let's just do okay. So essentially, what are all these things? So first of all, I see that I have a secondary material. Okay, so secondary is in my red area. I'm not necessarily sure. There's overlap. Okay, so with the secondary, I have to ask myself, is it strong or is it weak? And this is clearly a strong nucleophile because I have a complete negative charge on that sulfur. Okay, so essentially I know this is strong. Okay, and what is DMSO? So DMSO is a polar polar aprotic solvent. That's what it is, polar aprotic solvent. Okay, and what does that mean? Well, essentially there's no protons in that solution. So for instance, benzene. So benzene is considered a polar aprotic solution. And yes, there are protons on it, but they're not capable of being removed like in an acid-base fashion. So think about it. If I have a whole bunch of SH nearby, these protons are not going to be removed, and they're not going to be given to the sulfhydryl nucleophile. So that basically, what we can say is it enhances the nucleophilicity. Does that make sense? So essentially, like, the fact that I can't transfer protons from my solvent molecule to the main reagent is a good thing because it enhances the nucleophilicity. We're not quenching the nucleophile. For instance, like, let's just do hydroxide mixed in, methanol, excuse me. So say that my main reagent is going to be sodium hydroxide, like on the reaction line. Let's say I wrote this. Okay, the reason why this would not promote an Sn2 pathway is, yes, I do have my strong hydroxide nucleophile. However, it can grab a proton from the solvent, and then you get water. So now some of your main nucleophile turned into a weaker nucleophile. So you decreased the nucleophilicity by using a polar protic solvent. This is polar protic. Okay, so that's the whole point, is that this aprotic, solvent is going to enhance the nucleophilicity by preventing proton transfers, whereas here with the polar protic solvent, you are going to decrease the nucleophilicity by having these proton transfers, which quench your main nucleophile. Okay, so essentially, what you can imagine is this is a strong nucleophile, polar aprotic conditions. Basically, it's bimolecular. So this sulfhydryl group is going to come in while the iodine is still attached. But we're sterically hindered on the dashed face. So that means that the incoming nucleophile has to come in on the wedge, okay, on the wedge. And that is my main one product that I get, and that is inversion of configuration. Okay? So strong versus weak, again, that's easy to figure out. Okay, so strong versus weak. Really easy. It's just who has a negative charge, who doesn't. Strong is the negative charge guy. Polar protic. Any of the aprotic ones are like DMF, DMSO, acetone, acetonitrile, etc. I think these are like the only ones I can really think of off the top of my head. Those are all polar aprotic solvents. Okay. Basically, I want to do just one more example, and then I think we'll pick up on this more soon. So let's just kind of look at let's do the same exact thing, but let's just do it by okay. So we have this, main reagent, this tertiary chloride, haloalkene, and essentially, like, you're pretty substituted. So I'm thinking that this is going to go under Sn1 conditions, where we form that main carbocation intermediate, and then water can just come in and add, so that you would probably get, I know I keep switching colors on you guys, but you would get, and I'm skipping the deprotonation step. So essentially, you would just get this. Okay, so you guys all see that? So this would be the result of just nucleophilic substitution under the Sn1 pathway. All right, but going through this, let's think about the logic here. So sodium hydroxide is a strong nucleophile, and essentially what it wants to do is it wants to go through the Sn2 pathway. So what does that mean? Well, that negatively charged nucleophile wants to attack that carbon that bears the chlorine before the chlorine leaves. But it can't do that. Why can't it do that? I'm looking for one word in the chat box. Sterics. Boom. Sterics. It's too sterically hindered. So this is why maybe this should make a little bit more sense now. Sterics, that's right, scream it. So for tertiary, like that's why I can say every single time it's Sn1. Because you don't have room for a strong, there is no room for a strong nucleophile to come in, okay? To immediately replace it. There's no way that you can have a strong nucleophile just come in, attack this very sterically hindered center, and then kick off that leaving group. What you could do is wait for the leaving group to leave and then add something on. So that's what Sn1 is. Likewise, you can say for the primary condition, wow, we don't have time to wait for a leaving group to leave because the resulting carbocation would be very unstable. Can you imagine a primary carbocation? That's what not stable, okay? So that's why you can't have the leaving group leave on its own. What you need instead is some stronger nucleophile to come in and attack and kick off the leaving group for you, okay? So that's kind of the logic here. So we saw the two examples here. We were tertiary, we were pretty substituted. So we didn't have room for that strong nucleophile to come in. That's why we had a weak nucleophile. To ensure that it was weak, we used a polar protic solvent. You know, the proton transfer to the nucleophile reduces the nucleophilicity. And that's how you would get this nucleophilic substitution product, Sn1. Under the Sn2 pathway, we had a slightly less substituted product, material, excuse me, and we used a stronger nucleophile and a polar aprotic solvent to ensure that we had the strongest nucleophilic conditions we could. And then that basically has this, inversion of configuration at that center, okay? And that's, I think, where we'll stop for today. I know we kind of did a lot of new information. Just keep practicing with distinguishing between Sn1 and Sn2, and we'll pick up with more of this, and we'll do ranking problems and all that in E1 and E2 next time. All right, see you guys.